Hello, my name is Ryan Sunda. I'm a Math1a student, and I'm going to be talking about the indeterminate form 0 over 0. This indeterminate form occurs when you take the limit of a function of x as x approaches number n and get 0 over 0. To illustrate this, we're going to take a look at one of the problems from our problem sets. The limit as x approaches 0 of 1 minus cosine of 3x over x squared. Now, if you were to take the limit of this simply by plugging in 0, you'd get 1 minus 1 over 0 squared, resulting in the indeterminate form 0 over 0. Similarly, if you look at the simple function, the limit as x approaches 0 of x over x, you'd also get 0 over 0, indeterminate form. However, the indeterminate form 0 over 0 does not need to result from the limit as x approaches 0. It could approach from any value n, so long as you get 0 over 0. To illustrate that, we'll look at the limit as x approaches 5 of x minus 5 over x minus 5. So you get 5 minus 5 over 5 minus 5, which equals 0 over 0. However, in the case of all these limits, you cannot say that this equals 0. Although we got the limit of 1 minus cosine of 3x over x squared as x approaches 0 to equal the indeterminate form of 0 over 0, by looking at the graph of the function up here, as x approaches 0 from both directions, we can see that it doesn't actually approach the value 0. It approaches a number closer to 4.5. Similarly, we have these limits down here resulting in an indeterminate value of 0 over 0. However, when you take a look at the graphs of these functions, x over x and x minus 5 over x minus 5, which are actually, they share graphs, if you look at as x approaches 0 of this function, the function value is not at 0, which 0 over 0 may suggest, but rather it's at the constant value of 1. And as well with as x approaches 5, as the function approaches 5 from both sides, we can see that the function value is not 0, but rather that constant value of 1, which leads us to believe that while the indeterminate value of 0 over 0 may suggest to some that the limit equals 0, this is not the case, and as we can see in this graph, it's actually equal to 1. So why exactly do indeterminate functions such as 0 over 0 require more work? Saying the limit of a function approaches a point 0 over 0 does not actually give us enough information to determine a definable value for that point. As we've seen in the function graphs earlier, we cannot simply substitute a 0 over 0 with a value of 0. But actually we begin to look at the rate of change, or the derivatives of these functions, as a ratio, and how they interact with each other. And that's where L'Hopital's rule comes from. Without going too far into L'Hopital's rule, we actually have to take two derivatives of this function to determine what the limit as x approaches 0 actually is. So long story short, this is actually going to equal 9 cosine of 0 over 2, which is 9 over 2, and as we remember, is equal to 4.5, which we saw in the earlier slides. And this is also why the limits of as x approaches 0 of x over x and the limit as x approaches 5 of x minus 5 over x minus 5 actually equal 1, because the derivatives of x and in the numerator and x in the denominator equal 1, and likewise with x minus 5 over x minus 5.